Dr. Ranjani Parthasarathy is a professor in the Department of Information Science and Technology, Anna University. Her area of specialization is computer architecture and networks. One of her special interests is Indian language technology systems. She is actively involved in research in all the areas and has over 50 publications to her credit. She has about 25 years of experience covering both industry and academics.
Welcome to the UGC lecture series in computer science. We are looking at a series of lectures in computer networks. We have been looking at the network layer and its details. So, we will just take a look at one of the important topics in the network layer, which is IP addressing. So, we will be looking at different subnets and subnet masks, the idea of classless addressing that is used in IP addressing, and then we will look at the ICMP protocol. So, let us look at what we mean by subnetting. We are already aware of what we mean by an IP address. An IP address is a 32-bit address which is used to identify a node on a network. So, if you look at subnetting, what we do is normally an IP address has a network ID part and a host ID part. That is, you have a network ID which identifies a network, and within that network you identify a host. Now, when we do subnetting, what we are trying to do is you are trying to take a larger network and divide it into multiple subnets. So, when you divide into multiple subnets, to each of the subnets you need to provide an ID. So, that is what we mean by a subnet ID. So, now the entire address can be looked at as a network ID, a subnet ID, and then a host ID. Now, the moment you divide it like this network ID plus the subnet ID together become what we call as the extended network prefix. So, now these two together form the network ID and the rest of the bits form the host ID. So, let us take a look at an example of this and how this is normally specified. Now, when we have a network ID followed by a subnet ID being specified, since the subnet ID part is variable, that is, we do not fix the number of bits that can be used for subnet part, it can be varied, we need to have a mechanism of specifying which bits correspond to the extended network prefix and which bits correspond to the host ID. So, that is specified by means of what is called as a net mask. Now, the net mask basically has all ones in place of wherever you have the network ID and the subnet ID to be specified. So, if I have, for instance, so many bits specifying the network ID and the subnet ID, all these bits are referred to will have a value of 1, and the rest of the bits which indicate the host ID. In this example, for instance, 12 bits are used for the host ID, which would mean that 20 bits are used for the network ID. So, you will have 20 ones followed by 12 zeros as the network mask. So, this network mask basically is used to specify the network portion of the IP address. So, wherever you have ones here, it indicates that is the network part of the address. Now, let us look at how these different subnet masks are given and what are the different size of networks that we can have with these subnet masks. Now, note that if you look at this picture here, so you can see that subnet mask is specified again in the same dotted decimal notation that we use for specifying IP addresses. So, that is, I have 255.255.255.0. Remember, the 255 is with 8 bits being represented, it is all ones. So, you are talking about 8 ones here, 8 ones here, right, and then 8 ones in the third byte as well. So, 8 plus 8 plus 8, so there is 24 bits denote the network portion of the address, and the last 8 bits denote the node portion of the address. So, with this kind of an addressing scheme, we also denote it using a slash notation where you say slash 24. This indicates that from the beginning 24 bits will be ones. So, the rest of the 8 bits denote the node part of the address. So, if I have only 8 bits to denote the node part of the address, number of nodes I can support would be 256 nodes. So, the size of the subnet I would say is 256 nodes when I have a subnet mask of 255.255.255.0. So, similarly, if I have a subnet mask which says 255.255.254.0, note here that this this third byte alone has a value of 254. With 254, what will that essentially correspond to in terms of binary number? It would be 7 ones followed by a 0. So, which means if I look at all the ones that are over here, you will have 8 ones here, 8 ones here and 7 ones here. So, that gives me a total of 23 ones, a slash 23 notation, which would mean again that I have 8 zeros here and 1 0 in this byte. So, I have altogether 9 zeros. So, with 9 zeros specified, I am using 9 bits for my node part of the address. So, I have 512 nodes being represented by this subnet mask. So, a subnet of 512 node size will have a subnet mask which is 255.255.254.0. So, if you extend the same methodology or the same idea, you can see that if I have 255.255.255.192, this indicates that I have 8 bits here, 8 bits here, 8 bits here are ones, and here 192 is 1 1 followed by all zeros. So 2 more bits here are ones. So I have 26 bits as ones and the rest of the 6 bits. So I have a 64 node network that is specified by this. So by looking at the subnet mask, you can identify the subnet size, and given a subnet size you can identify what the subnet mask should be. So now how do we use these masks when you actually operate to obtain the net ID and the host ID? So let us look at that. So the network address is found by applying the default mask to any address. Now what do I mean by saying I apply the default mask? What we do is a bitwise AND with the address. So when you do a bitwise AND with the address, you will get the net ID of the block and it will set the host ID to zeros. So let us take a look at that. Okay. So what I said is network address is given by IP address, whatever address you have, AND it with the net mask. Okay, that will give me the network address. If I want the host ID, all I need to do is take the IP address and AND it with the NOT of the net mask. Remember, the net mask has got ones where the network is and zeros where the node part is. So if I invert that, I will get ones where the node part is and zeros where the network part is. So when I AND a 0 with the IP address, the only bits I get will be the node part of the address. So that is what you will get. So let us take this example to make that clear. Suppose my IP address is 203.4.11.135 and the net mask is 255.255.255.0. This means all ones over here and these are zeros. When you do a bitwise AND of the IP address and this net mask, okay, remember the 255 is all ones. So when I AND all ones with 203 and I do a bitwise AND, I will get back my 203. So you will get 203.4.11.0. Remember 0 when ANDed 135 will remove this entire 135 and make it all zeros. So you get 203.4.11.0 as your network address. So this will correspond to the network part of the address, and if I want the node that I am referring to, then I need to remove all these and retain only the 135. So I am doing an AND with the inverted value of the network mask or the complement of the net mask, and what you will get will be all these will become zeros and you will just get your 135 as your host ID. So the network ID and the host ID can be obtained by applying this net mask or the inversion of the net mask on the IP address. So another example, suppose I have 203.4.11.135 and now the net mask is 255.255.254.0. Okay, note that the net mask here is different and net mask there is different. Okay, now this refers to a network where you have 256 nodes in the network. This refers to a network which has 512 different nodes in the network. So let us look at what will be the network ID over here. So here my network ID is obtained as the IP address, which is this value 203.4.11.135, and it with the net mask, which is 255.255.254.0. So when you do the AND here, you will find that you will get 203.4, the first 2 bytes will come as it is, but the third byte over here 11 when ANDed with 254, you will find that the last bit is lost, but you will retain the 10. 11 here would correspond to 1011. When it is ANDed with 254, you will get 1010 as the value here, so which becomes 10. So you get 203.4.10.0. Note that this will be the net ID for the subnet ID for this network address when you have the mask as 255.255.254.0. And similarly, the host ID here would be IP ANDed with the invert of the net mask. Since the net mask here is 254.0, you will get that one last bit over here will also come into effect. So you will have 1.135, which actually corresponds to the 391st host on this particular network, or 1.135 will identify the host part of this particular network address. So this is basically how we use the net mask to determine which part is the host ID and which part is the net mask. Another example on the same thing, but now we have our net mask as 255.255.255.128. So you can see now that when I do the mask of the IP and the net mask, the network ID now will be 203.4.11, this will come in as it is, whereas 135 is added with 128. Okay, so this is 128 basically is 1 followed by all zeros, 135 will 1 followed by something else. So all the other bits will be lost, the 1 alone will be retained. So you will get 203.4.11.128. So that is your subnet ID. Now the host ID will be obtained by doing the mask with the inverted of the net mask. So you get 135 basically is ANDed with 128, and the value you will get will be 7. All the other bits will go to 0 except the last 7 bits. So the last 7 bits will give you a value of 7. So this is how we obtain the net mask and the host ID in this example. Now, coming to the default masks that can be used for the standard classes that we have. Remember, we talk about a classful addressing in IP, where you have a class A address which has 8 bits in the network portion and 24 bits in the node portion. So, this can be specified again in the dotted decimal notation. This address would be specified in the mask would be specified as 255.0.0.0. So, you can use the same subnet mask idea to also specify our standard class A, class B and class C networks. So, if you take a class B network, you can see that this will have 16 bits of ones and 16 bits of zeros. So, that is, the 16 bits indicates your node part and these 16 bits indicate the network part. So, the mask corresponding to that would be 255.255.0.0, and in the slash notation you can just represent it as slash 16. So, a class C network similarly will have 24 bits for the network part of the address, 8 bits for the node part, which is represented as 255.255.255.0, and you specify a slash 24 in the slash notation. So, we can see therefore that the same mask based addressing mechanism can also be used for our class based addressing scheme. Okay. Now, we will take another example of how different length subnets can be used in a given network itself. That is, let us say I have a network address of 203.4.1.0, this is my normal network address that is given to me, and this address is being subnetted now into multiple smaller subnets. But what I have here is each subnet has got different number of nodes in the network. Okay. So, I have one network which has 62 nodes, another which has 62, another which has 30 nodes, another which has 14 nodes. Now, corresponding to this, you can see that I can have different subnets, each with a different mask. So, 62 would correspond to having a node which can accommodate up to 64 hosts, right. Up to 64 hosts would mean that I need 6 bits to specify the network, the host part of the address. So, if I use 6 bits for the network for the host part of the address, 26 bits will be used for the subnet part of the address, for the network part of the address. So, you can specify this as 203.4.1.0/26, and the net mask for this will be 255.255.255.192. Note that this 192 refers to first 2 bits being 1 and the last 6 bits being a 0. So, the same network mask will be used for these 3 networks, but the network address will differ, because remember that they all have to go to 3 different addresses. So, this will give me a subnet address of 203.4.1.0 corresponds to the first subnet, 203.4.1.64 corresponds to the second subnet. So, this essentially tells me that 203.4.1.0 to 203.4.1.63, those 64 nodes, those 64 addresses correspond to the first subnet. Similarly, 203.4.1.64 all the way up to 127 will correspond to the second subnet, and so on. So, you can see that the third subnet similarly will have values from 128 to 191, and all of them will come to the default subnet. When you apply the subnet mask, they will all come to the subnet number of 203.4.1.128. So, similarly you can see that when I have only 14 hosts in the network, then my subnet mask will be 255.255.255.240, and it can be specified as a /28 notation, essentially meaning 28 bits are used for the network part, only 4 bits are used for the node part. Okay. So, this is basically how you can have variable length subnets also specified for a given network itself. Okay. Now, given that we have this subnetting scheme, let us look at how the routing actually is done with this subnetting scheme in place. Now, look at what will happen to routers which are outside the organization. All routers which are outside the organization view the network as one entity. Okay, that is one entry for the entire network. Now, when you actually come to the router at the organization is subnet aware. So, there it will identify that these actually have to go to different subnets. So, it is only at the router which is connected to the organization that the subnet mask will actually be applied. For the rest of the network, the rest of the routers which are outside the organization, all of them assume that all these different subnets belong to the same single network. Okay. And when you actually come to the router which is at the organization, it is there that the subnet mask is applied to identify the subnet. So, let us look at what an example of how that is done. Take a simple example. A router outside the organization receives a packet with destination addresses 190.240.7.91. How does it find the network address to route the packet? So, just take a quick look at this solution for this. The router will follow 3 steps. One is it will first look at the first byte of the address to find the class. You can see that it is a class B address. Then it will apply the default mask to the class B, which we know we just saw is 255.255.0.0. When it does that, it gets the value of 190.240.0.0. So now the router looks in the routing table to find out how to route the packet to this destination of 190.240.0.0. Okay. So this is basically what a router will do, a router which is outside the organization will do. Now let us look at what happens at the router which is connected to the organization. Okay. So let us take a look at this example. So a router inside the organization receives the same packet with destination address as 190.240.33.91. Now how does this find the subnet address to route the packet? So what does this have to do now? The router follows these 3 steps. The router must know the mask. Okay. Now the mask would normally be specified in the routing table. Say it is /19, okay, which is 255.255.224.0. So what it will now do is it will apply this mask to this address. So when it applies this mask to the address, it gets a value as the subnet address it will obtain will be 190.240.32.0. So now it knows that 240.32.0 corresponds to a particular interface on that particular router, and that is the subnet to which it has to route it. So the router looks in its routing table to find the interface to reach the subnet. To which subnet we are talking about 190.240.32.0. So this is the subnet to which this particular packet will be routed. So this is the difference that we have between what happens at a router which is outside the organization and the router which is at the organization, which is aware of the subnets and it passes it to the correct subnet. Okay. The same idea of mask based addressing has also been extended to get what are called as classless addressing mechanisms. Now note that in with the class based addressing mechanism that was used in IP, people were running out of addresses. We were running short of addresses because there were a lot of wastage of addresses taking place in the different blocks of addresses that we have. Typically this is happening mainly in the class B addresses. Now to the moment this idea of a mask was introduced, the same idea has now been extended to have what's called as a classless addressing scheme. So let's look at how this classless addressing scheme is achieved. Okay. So what we do in classless addressing is the following. Essentially, you are extending the idea of using masks to specify the network portion of the address. So remember that in the class based addressing scheme, we identified whether it was a class A, class B or class C by just looking at the first few bits of the address. Now you no longer do that. What you do is, and class A, class B and class C, we had fixed number of bits for specifying the network part and the node part. You no longer do that now. Instead, the number of bits which specify the network part can be variable, and the number of bits that you have is actually specified by means of this mask. Same idea as to what we use in subnet mask is now used for a classless addressing mechanism, and again we refer to that as a mask again, or a network mask. Okay. So what we do here is, it is not necessary to use classes to identify the network portion, we only use the mask, and the network ID can be of any length. Okay. And this addressing scheme is referred to as the CIDR, or the classless interdomain routing, CIDR, which is normally pronounced as CIDR. It is called as the classless interdomain routing scheme. So you will take a look at how this CIDR addressing mechanism works. So in this CIDR addressing mechanism, one of the advantages that we have is using this mechanism is that it allows aggregation of the network addresses. That is, addresses with the same prefix can be grouped together. We will take an example of how this is done. So the result of this kind of a grouping together is that it reduces the number of entries in the routing table. Say for instance, in a core router, I have a number of entries, but all these entries are actually pointing, are all supposed to be sent to a network which is in the same direction, let us say. So now you need not have different entries for each of these network addresses. Instead you can group all of them together and have just a single network address which points to this particular direction. So you can reduce the number of entries in the routing table, which essentially helps us to make the routing process faster, because you do not have to go through a longer list. It becomes a shorter table that you need to look at. And the network portion of the aggregated address is specified by once in the CIDR mask. So let us look at what happens over here. So in the classless IP address scheme, what we do is, you have the host ID specified by n bits, and the rest of the 32 minus n bits will specify the network ID. So again, so for instance, if you have a network of 50 hosts, you will use 6 host ID bits, so /26 network, which can specify up to 62 hosts, and the net mask would be 255.255.255.192. The same concept that is used in the subnet masking scheme. Okay. So a network of 300 hosts similarly will use a 9 host ID bits, so which would indicate a /23 network, and this can go up to 512 hosts, or 510 we say, because there are 2 values of all zeros and all ones which are treated as special addresses. So up to 510 hosts we can support on this network with a net mask value of 255.255.254.0. Now when you do this classless allocation, what we can achieve is, as I said, you can do this aggregation of network addresses. That is, we reduce the size of the routing tables on the backbone routers, okay, and you can do this if the IP addresses are allocated regionally, okay, and then you allow the aggregation to take place. Okay, so let's look at an example of take an example of how that is done. Suppose that this is just an example. Suppose I have the addresses 194.0.0.0 to 195.x.x.x as addresses which are assigned to say Europe, and 198.0.0.0 to 199.x.x.x goes to North America, and so on. Okay, 200 to 201 is another place, 202 to 203 is another place, and 204 to 223 is reserved for future use. Okay, let's just leave it at this. Now a backbone router in North America may only need one routing entry for all of Asia specific, which is 202, because Asia specific, note that it is 202.0.0 to 203.x.x.x. This entire range of addresses can be covered by just a single entry which says 202.0.0.0/7. Okay, so with just this 7 bits used for the network part of the address, this entire range of addresses can be combined as one single address. Okay, there is 202.0.0 to 203.x. You have a whole large number of different addresses which are actually covered by this range, but all of them can just be covered using this one single entry. So this is the major advantage of this classless addressing mechanism that is used. Okay, so if you look at a routing table with CIDR, this is what it will look like. So for instance, you may specify the net followed by the mask length and the next hop. So the net value here again it may be mentioned as a hexadecimal value for, or maybe decimal, may be given as a decimal value. In this example, typically we use the hexadecimal value because it becomes easy to understand, to specify the ones and zeros over there. So C4 stands for the hexadecimal value of the first byte, C4.50.2.0/23. If this is the address, we say it has to go to interface 0. This is the next hop address just specified at the router. So similarly, if this is the address /2020, after applying a mask length of 20, if this is the value you get, it will be sent to interface 1. Similarly, C4.60.0.0, if you apply a mask value of 12 and you get this value, it will be sent to R2. Now we also have something called default routers which are typically used. Now these are addresses to which it will be sent if it does not match any of the others. Okay, so if that is normally what we do is we use something called a longest prefix match. So you will see that if I take a 0.0.0.0.2, most of the addresses will definitely match this address because you are ANDing with just 2 bits and the rest of the bits are all zeros, and you may end up with all zeros very easily. So when you have 2 different addresses matching to the same a single address matching to 2 different values over here, we always take the longest prefix. Longest prefix in the sense, more number of bits match, then that is the value to which it will be sent. Okay, so you have, in fact in this example there are 2 default routers which are specified. So addresses which do not match the correct entries which are specified here would either be sent to this or this depending on which address they matched. Okay, this is typically how a routing table with CIDR would look like. Okay, so now having looked at different network addressing mechanisms and the IP protocol in detail, we also need to look at a companion protocol which is called the Internet Control Message Protocol or the ICMP protocol. Now the ICMP remember that IP is only a best effort delivery and does not really take care of errors or any such thing, but it uses this ICMP companion protocol to report errors if they occur. Okay, so that is the importance of this ICMP protocol. So it serves as the error reporting protocol for the IP protocol. Okay, so let us look at how this ICMP protocol basically works. Now the ICMP protocol, it is a help protocol as I said that supports IP with facility for simple queries and for error reporting. So let us look at what it will do. So this ICMP message itself is encapsulated as IP datagrams. So they are sent as, so you will have an IP header for this and the ICMP message will be carried within the IP header, within the IP data part. Okay, so the message format it is a very simple format. You just have a type field, a code field, a checksum, and then there is some additional information which is sent. The header, if you look at, it's basically, as I said, a 4-byte header. The type field which will identify the type of the ICMP message, a code byte which will specify what is the subtype of the ICMP message, and a checksum, it's a 2-byte checksum which is similar to the IP checksum, and the checksum is calculated over the entire ICMP message. Okay, and if there is no additional data, there are 4 bytes which are set to 0. Each ICMP message is at least 8 bytes long. So, this is the normal format of an ICMP message. So, let us look at some query messages that I used. So, the query messages basically have a request and a reply kind of a format. So, when a host can send an ICMP request and the host or a router can send back an ICMP reply. So, a request will be sent by a host to a router or a host, and a reply will be sent back to a querying host. So, this is one type of ICMP message that normally supported. Examples of the ICMP query type of messages are echo request and echo reply. Okay. So, this is a message which is used to just check whether the router or a node at the other end is available or not, whether it is up or not. You can just check that. Now, the ping command which we normally use to find out if there is another node is available or not, it basically uses this echo request and echo reply facility which is provided in the ICMP protocol. Okay. Similarly, we also have a timestamp request and a timestamp reply. Now, this is used to find out what is the you request for the timestamp, find out what is the time at which it was received at the other end, and timestamp reply is sent which says this is the time at which I received the message and this is the time at which I am sending you back the message. So, you kind of get a complete information about how much time it takes for a packet to go from one place to another place and then come back to you. So, these are used for some measurement purposes and for checking various things. Similarly, there are other messages which are used for router solicitation, router advertisement and so on. Okay. Now, let us take a look at this echo request and echo reply. As I said, this is used in the ping command. So, an ICMP echo request will be sent by the host, and the reply basically you can see it is an echo, right. And what do we mean by echo? Normally whatever is received here will just be echoed back, will be sent back. So, that is called as an echo reply. So, when you send an echo request, you get back an echo reply, then you know that this host is up and ready, and you can send data to that particular host or router. Now, if this is not ready, you will not get back an echo reply, and that can be used by this host to identify that this node is not available. Similarly, if I have a timestamp mechanism that I just talked about, so you can see what happens in this case. The sender sends a timestamp request and the receiver sends back a timestamp reply. The time is normally measured in milliseconds after midnight UTC. They use something called universal coordinated time of the current day, and that is how the time is measured. So, sender sends a request, receiver responds with a reply. Now, if you look at the format of this, it will look like this. You will have an identifier field and a sequence number field. Now, this identifier and sequence number are the ones which are used to connect a request to a reply. And then you will have a 32-bit sender timestamp, a 32-bit receive timestamp, and the 32-bit transmit timestamp. So, at what time the sender sent it, at what time it was received by the receiver, at what time it sent back the reply. So, this is the information that you have in a ICMP timestamp message. So, the other category of messages that we have in ICMP are the error messages. Now, these are very important because error messages report error conditions. Okay. So, when an IP datagram is sent, if the IP datagram is discarded or something goes wrong, okay, IP does not do anything, right. So, what it will instead do is it sends back an ICMP error message. Okay. So, it is typically sent when a datagram is discarded, and this error message may be passed by ICMP to the application program. So, when we do an error message is sent, look at how the format of the ICMP message now looks like. What it has is, it has the ICMP header, plus it also has some information about the packet that was dropped or that was not delivered properly. So, you have the IP header plus 8 bytes of the payload of the packet that was not delivered correctly. Okay. So, that information of which packet went wrong, okay, delivery of which packet went wrong is sent in the ICMP error message. Okay. So, it will have the error message will include the IP header and the first 8 bytes of the payload, which will typically tell you whether it is UDP packet, TCP packet, what kind of packet it was. So, you get some information about which packet was not delivered correctly. Now, when you talk of destination being unreachable, there are different types of destination unreachable which ICMP detects. One is that the network is unreachable. The second is the host is unreachable. You are able to reach the network but not the host. Within the host, the protocol is unreachable. That is, you are not able to reach the UDP or TCP protocol, but you are able to reach the protocol but the port becomes unreachable. Okay, these are all different types of unreachable mechanisms, messages that are sent. Similarly, you may have something like fragmentation needed but the DF flag was set. The don't fragment flag was set. You are not able to send the packet forward because you have to fragment it in order to send it. These are all different types of error messages that ICMP reports. So, other common ICMP error messages are time exceeded, which says the TTL has expired, reassembly timer expired, redirect the route, then parameter problem. These are different types of error messages that are used. Okay. So, to summarize, what we have looked at today are two different aspects. One is subnetting and the classless addressing which are used in the IP addressing mechanism, And then we also looked at a basic overview of the ICMP protocol, which is an error reporting protocol. So, we saw that it supports two types of messages, one is a query based messaging and the error reporting messages. A few questions for you to take a look at what has been done today. Question number 1, how many subnets can be obtained with a mask length of 19, that is /19. Identify the subnet address and node ID of the following IP addresses: 156.23.78.26 with a mask of /20, 194.34.56.78 with a mask of /24. What is the idea behind CIDR? Question number 4, what are the benefits of CIDR? Question number 5, what is ICMP used for? Question number 6, which ICMP message is used by the ping command? Question number 7, what happens when a packet is dropped at a router? Thank you.